you for the introduction, and thank you for the invitation. So I'm going to talk about scientific computing in Lean. And so the first question you might ask is, why Lean for scientific computing? People use Python, Julia, Fortran, C++. Why on earth would I use Lean? And it's a very good question. And my two-sentence pitch is that the language of science is mathematics, and then Lean speaks it. And if you try to combine those two things, then something interesting will certainly come out of it. A little bit more involved argument why I think it's an interesting thing to do is that, so let's look at like how we do scientific computing. So we first observe the world, we formulate some kind of a model about the world, and we want to model the world on a computer. So what we need to do, we need to turn the model into something that we can actually implement on a computer. And I would like to point out that these two steps are usually done by hand. Then the next step, we need to kind of the discretized model, we need to turn it actually into computer code. And then the computer can run the code for us and kind of make a prediction about the world. I'm really happy about the state of this process. So what I would like to ideally do is that we directly write down the model to the computer. And then the computer can somehow take all those equations and turn it into code that we can actually execute on the computer. And of course, this is too bold ambition. So my hope is that actually we write down the model in the computer, and then the computer will get into dialogue and help the computer to turn it into executable code. And I think Lean is like a perfect language for this because it can really talk about all the abstractions on every level. So kind of more concrete, which kind of features of Lean I think are very interesting, is that in Lean, unlike in many other programming languages, you can talk about mathematical abstractions and like you can write down like functions that are really not computable. You can write down integrals, derivatives, functions that return a solution of differential equations, and you can work with them as normal functions. And I think that's really cool. And this way you can kind of mix all the symbolic and numerical methods. And traditionally, all the programming languages, they usually split into two divides that you have like Maple, Mathematica, which are more symbolic on the level, and then all the other one like Python, Julia, or MATLAB that are more on the numerical level. And kind of the ability about talking about the mathematical abstractions, it can really seamlessly bring these two worlds together. The next thing which is really nice is all the machinery to allow for interactive proofs. Is that I feel that we can kind of twist it and slightly abuse this to build interactive computer algebra systems or source code transformations. Or another, I think, cool idea would be to writing new programs as a specification and then interactively turning into implementation, or doing a code optimization. So there are a couple of domain-specific languages which allows you to write down code in a very naive way, and then just applying some kind of code transformation, you can turn it into highly optimized code. And of course, Lean is an interactive term improver. So the interesting thing about using Lean is that all of this can be somehow formally verified and proven correct to a certain degree. To kind of comment about all these points, I will show you a bunch of examples. So I prepared like these 4 examples. And so I will show you how to do a symbolic and automatic differentiation. And this, you can kind of look at it in general as some kind of a general framework for function transformation. And I don't know if you have experience with using a very popular machine learning framework, JAX, then it all revolves about function transformation. So I think in Lean we can implement something very similar. Then the next example will be about synthesizing approximations. So yeah, as I said, many operations inside of the computing involve solving differential equations, computing integrals, but none of these things can be computed exactly. So it would be nice to have some kind of a way how to turn these things into approximations and have a control about how these approximations, like how well these approximations do, or which parameter do we actually need to increase such that we get a better approximation. Then the next step will be optimizing array expressions. You in machine learning right now, you write down a bunch of tensor contractions or convolution and stuff like that, and quite often you want to optimize these things. So either you write them in excruciating detail how you do everything, or you write the naive implementation and then you turn into something more performant. And then lastly, for the last couple of months, I have been exploring probabilistic programs, and I feel that in this domain, Lean can also have a very interesting application. So I will show a few examples in that. So let me talk about symbolic and automatic differentiation now. So what is automatic differentiation? It's, very roughly speaking, is a process of taking a function, for example, this function foo, which is written as the number squared. We would like to somehow automatically create a new function that computes its derivative. And that has many applications. This automatic process of computing derivatives has many applications in machine learning, optimization, all scientific computing. So, and how I approach it in Lean is that, for example, MATLAB has a definition of a derivative. So the Fisher derivative of a function f at point x is some linear function that like as closely as possibly approximates this function. And if such a linear approximation exists, then you return this. Otherwise, you just give up and then return 0. Okay. And I would like to use this definition to somehow do symbolic and automatic differentiation. So if you use it kind of naively, for example, I take this function foo x squared, and you just apply the derivative to this function, then you are forced, because this function is completely uncomputable. It just states like, oh, if this derivative exists, then please return it. So defining this function just as taking a derivative of foo is no good, because you are kind of forced that this function is non-computable and we cannot execute it. So what I wrote is like a specialized tactic that computes this derivative. And how you do it is that you take this expression, and then there is this macro rewrite by, which looks at this expression and rewrites it using this tactic. And this funtrans tactic is a general function tactic for function transformation. So how would one set up this tactic for differentiation? It's very simple. So you just add a bunch of attributes. So at the definition of the derivative, you just mark it that it's a function transformation, and then you go over MATLAB effectively and find all the theorems that says, oh, the derivative of this function is this function. For example, yeah, the derivative of the linear function is a linear function, of identity function is identity function. The derivative of composition is, if you look at it long enough, then you realize this is just a chain rule. And then derivative of addition is just an addition of derivative. And you just go and you mark all these theorem with a funtrans attribute. And so let me show you the code, how to actually use it. So here, for example, I define the function foo. Now it depends on two parameters, x and y. And I would like to define a new function, which is just a y derivative of foo. And I already also defined like a nice to use notation. So here I say, I take the expression foo of x and y, and I want to differentiate it with respect to the y prime, and then evaluate it at point y. If without all this, the compiler would complain that this definition is non-computable. But adding this macro rewrite by is just we look at this expression and we will kind of transform it until we get something that is actually computable. So the first step is to unfold the definition. And now it's expressed in terms of addition and like multiplication, powers. Then we can just apply the tactic funtrans, and it computes the desired answer. So now this function is really defined as this expression, and it's perfectly computable. And, it's kind of nice. So yeah, here's an example of, yeah, that's the same example of a derivative. So we want to compute the derivative of x squared. We just apply the, yeah, so here's the what we want to compute. And if I click after the tactic, then it shows the result. So derivative of x squared is just 2 times x. And I have a bunch of different function transformations. So there are kind of different flavors of derivative. So either you can take a normal derivative, effectively directional derivative, or there is a gradient. So if you have a function from, for example, from Rn to R, we often, during optimization, we want to compute the gradient of this function. So if we compute a gradient of the norm, the L2 norm squared, then we should get just the 2 times the vector. So if I just compute it, yeah, we get 2 times the vector. And then there is a forward mode and reverse mode automatic differentiation, which is kind of special. It's very similar to normal differentiation, but it's really specialized so that it differentiates code efficiently. So that, for example, if I have some lead bindings, then and I would compute the forward derivative, which is just the derivative with this kind of arrow going forward. I compute the derivative, then the tactic is kind of smart enough that it sees the bunch of lead bindings, then it kind of generates a new lead binding such that the resulting code is efficient. And the similar thing happens with in the reverse mode. And the only difference between forward mode and reverse mode is effectively if you're computing a Jacobian of the function, whether you want to multiply the Jacobian from the left side or right side. And in different application, one is preferable than the other. And the tactic functrans is really general, so it doesn't have to apply only to differentiation. So here's, for example, here's an example when I take a function and this function just adds 1 to x, and I want to compute the inverse of this function. And I just call this tactic, and it transforms it into a function that removes 1. So the support for computing inversion is very limited, but it's very useful in certain scenarios. Okay. Right. So that's all about automatic differentiation. So the next example I want to show you is that how can you use lean to synthesize approximation. So inside of computing, we very often solve systems of equations or integrals solving ODEs, and we have to resort to approximated methods. And I would like to have some kind of very generic way how I can construct these approximations, and then have very kind of fine control over what approximation I used, and then what are the parameters of the approximation such that I can improve the approximation. So to give you an example, so I would like to compute the square root function. So I define a function square root of y. And I can define it just, I take the function that computes the square, and I take its inverse on y. Of course, the taken inverse is not computable, so this is just a specification. And now I would like to define a function my square root, which is an approximation of this function square root. And this object, effectively, this object, what I would like to for this object to hold is some function that computes the square root in some approximate sense, and it holds information about the approximation that I used, and it, for example, can provide me a proof that if I take a limit, for example, in the number of steps of the solver, then I actually reach the promised value. So there's this mysterious parameter p, and what this p is, it's a filter over the approximation parameters. So the approximation parameters are exactly number of steps or the tolerance and stuff like that. And the filter is, if you're not familiar with the filter, this effectively tells you how you're supposed to take a limit over this object. And then now you can use this object approximation by providing some concrete values of the approximation parameters. So for example, yeah, I specify the absolute tolerance used in computing the square root, and then I evaluate it on 2, and I get this answer. And then if I specify that the iterative process computing the square root is allowed to use only one step, then I get very, very bad approximation. And then the whole, but yeah, I still don't have a like very precise definition of this object approx. But my kind of hope is that I would then get a theorem that guarantees me that for every y, if I take a limit of this function's my square root, I actually get the answer. So let me show you it in the code. So, right. So how I define the approximation is that I say, instead of def, I define an approximation, and this approximation should be of this function. So this function exactly, I take x squared, I compute its inverse. So this thing is computing its square root, and my square root should be an approximation of this function. So now we enter a tactic mode, and in this tactic mode, we will construct slowly this approximation. So now you can see that the goal is this object approx. Here, we still do not know which approximation we chose, so we don't know which will be what kind of the approximation parameters we will choose. This will be determined only throughout the process of choosing approximation, and the function we want to approximate is this is the square root function. So the first step, what we do, we just focus on the function, on the square root function, and then we say that. So I have a theorem that says, if you want to approximate the inverse function, you can solve some system using a Newton solver. So if I apply this theorem, then you can suddenly see that I have this Newton solver. I have the objective function, and then here's a function doing the. If you run a Newton solver, then you need to compute the inverse of the derivative of the function you are actually inverting. So here is exactly, I have this function, I compute a derivative of the x squared, and I take inverse of it, and I plug it into the Newton solver. Okay, and then what we also do, we take a limit. So, right, because we are rewriting the goal exactly. So we got the result is we have to take the limit such that like we take the infinite number of steps of the Newton solver to get the right answer. So the next step is that we want to get rid of this limit. So there is this static approx limit, and this static effectively looks at the goal, and if it finds a limit, it removes the limit and stores the information in this approx object. So if I click this, oops. Yeah. Then the limit completely disappears from the goal, and we are left only with the Newton solver. And the last step we need to do is that here in the Newton solver, we're still providing the derivative of the inverse of the Jacobian, and we need to compute these things. So we do this by calling the tactic autodiff. So first we compute the derivative of x squared, which is just 2 times dx times x. And then the next step, we need to compute the inverse of this thing. So we just already somehow can compute inverses as well. So it just computes the inverse. So and now at this point, this function can be completely executed and compiled. There is nothing that is non-computable. So this whole kind of command is happy, and we can just run the function. So yeah, I can call the function my square root. I can provide the tolerance or max steps, and yeah. So if I provide reasonable tolerance, then I get the result, like very good approximation of square root of 2. If I limit the Newton solver to a single step, I just get 1.5. Right. So this was kind of very basic example of this idea of taking a specification of a problem and then deriving a program that is approximating the specification. So I can give you a more complicated example for solving differential equation. So here I will construct an approximation. I call it solver. And what this does, it's approximating a solution of differential equation. And if you actually you might recognize this. These are just Hamilton equations. So here there's a function h. I define some Hamiltonian which corresponds to some physical system. And I want to solve a differential equation corresponding to this Hamiltonian system. And then again, we can look at the steps. So we want to find an approximation of a solution of differential equation of this Hamiltonian system. And the steps are, you unfold the definition of the Hamiltonian, you compute the derivative, you get some s. Now there is still the function ODE solve, which is completely non-computable. So we need to approximate it by some time-stepping scheme like Runge-Kutta. So what we do, we just focus on the function ODE solve. And here's again a theorem which says, in the limit, you can approximate the function ODE solve by iterating, for example, Runge-Kutta numerical scheme. So we rewrite this. Again, we get the limit here. So we call the tactic approx limit, which somehow consumes the limit and stores the information about the approximation process in the object approx. And then here, for example, in the code, we can just use the function solver to call it with appropriate settings. And because Lean has very cool integration into VS Code, we can visualize it. So the physical system was corresponding to wave equation, and I can just run the simulation directly in the code editor. And I think I'm doing reasonable on the time. So here's another example of the same flavor, is that, for example, we would like to shoot a cannon. We would like to figure out the initial velocity with which we want to shoot a cannon, and we would like to hit the target. So the red dot is a target we want to hit, and we are shooting from the origin, from the center, and we want to figure out the initial velocity we want to hit. And the specification of this problem is that, again, we are creating some approximation. I call it aim to target. And the important part is this line, is that there is a function shoot, which, given the time and the initial velocity, it returns the position that the cannon hits at the time t. And we compute the inverse of this function and evaluate it on the target. Therefore, this thing should be equal to the initial velocity such that we hit the target. And the function shoot is just solving the differential equation corresponding to ballistic motion. And here's somewhat lengthy kind of instructions how to turn this specification into implementation, which is just somehow discretizing the differential equation. When you differentiate, for example, the solution of different equations, you get two different equations, one which goes forward in time and the other goes backward in time. So you have to choose how you discretize these different equations. So yeah, that's a bit involved. I'm not gonna through all of it, but yeah, you get a function that you can run, and here you can kind of see the optimization process, how it improves the initial velocity. Okay. So, right. So that was about synthetic approximations. So the third example I want to show you is how to optimize, how to effectively write interactive optimizer in Lean. So one of the kind of the simplest operations in numerical linear algebra is to take a number and two arrays and multiply one array and by the constant, and then add the other array to this. So if you would write this naively, then each of these arithmetic operations corresponds to one for loop. So if you take x an array and you multiply it by a, then you have to run through every element of x and multiply it by a. And then when you do the addition, then you again effectively have to run through every element of those arrays and add them together. This is of course inefficient, so there exists exactly a specialized function which is usually called sexpay. And the idea is that you really want to fuse both of these arithmetic operations into one operation. So for example, you want to say that you take the array x and you map every element of the array x by, you multiply it by a, and then you also add the y of I. So I would like to somehow automate this in Lean. And I can do this, I define a specialized macro, definition optimize. And what you can say is that please optimize this definition of this function. And here are again some tactic which will do optimization. So let me show you this in code. So right, I define here the function sexpay, which computes this, and we define this. And now we say, please, we want to optimize this function. So now we turn into tactic mode, and we see our goal is this expression. So what we can do, we just unfold all the definition of addition and multiplication, and we see that it's effectively composition of two map operations. So yeah, we first exactly map x by multiplying by a, and then we run another map to do the addition. This is, of course, complete waste, so we would like to fuse these two map operations together. So I formulated a bunch of versions of if we run two map operations in sequence, we can always convert it and squish it to a single map operation. So now I can just call this, and I get a code that has a single call to a map over the whole array. Therefore, we reduce the operation from effectively 2 for loops into a single for loop, and we should get a more efficient implementation. And this macro def optimize creates a new definition, sexpay.optimized, and also a theorem, sexpay.optimized rule, which is saying just that the original function sexpay is equal to the optimized one. And also what this macro does is it actually marks this theorem such that the compiler applies this rule while it's compiling a code. So the compiler will, each time it encounters expression like this, it will replace it with this. So another example of optimizing like array expression is that if we do matrix vector multiplication, you can write it like in very kind of neat mathematical notation. The only unfortunate thing is that I do a very kind of abstract way of dealing with array indices and stuff like that. So anytime you for example, have a matrix and you index it by a pair of numbers, that what the compiler does, it actually creates a pair of two indices. And this is very bad for performance because internally Lean implements pairs of objects. It kind of boxes them, put them on a heap, and the pair just contains a pointer stores this. And this is like very bad for performance because if you have just like two matching numbers or two integers, you really want to store them together on a stack or something. So we completely want to avoid heaps. So doing this is not very good, but I would like to still write the code in this way. So the way around it is that exactly you write the code this way, and then you just say, please optimize this definition. And then you effectively force you directly tell the Lean which definition it should unfold. And if you look at the result, then it takes the matrix A, looks at the internal data structure, and the data is effectively the linear array where it kind of takes the whole matrix which is square and linearize it into a linear continuous block of memory. And then it computes the linearized index access. So you're directly accessing the memory in the correct position. And all the kind of indirect abstraction, which I deal with to kind of support very complicated indices, is completely eliminated. So, and of course, writing this every time is very tedious, so you can just easily define a new tactic, which is called optimize index access, and you just get the desired result in one shot. Here's another example. When you take a dot product of two matrices, for example, here you're running a sum over all the pairs of possible indices. Of course, again, you want to look at the matrices as just a continuous block of memory and run over all the indices from like 0 to n times m. So again, oops. Right, I have here I do the dot product. And if I call the tactic optimize index access, you can see that it will actually turn into sum over all the numbers from 0 to n times n minus 1. And here again, I'm just accessing the kind of the linear, I'm accessing the data in the linear fashion. So there should be no overhead over any kind of complicated index accesses. Right. So that was all to how you can kind of define a custom optimizer in Lean. So the last example I want to talk about is probabilistic programming. So when I want to work with a probabilistic program, I want to kind of say that this variable is random. So I define some specialized structure, rand. And if I say the rand of x, so the x is of type rand of x, it means that it's really the x is of type x, but it's somehow randomized. And it's kind of interesting how you define this object. Is that so? The rand of x contains three fields, and the first two fields are completely a specification. So effectively, the mu, it tells you have some kind of a measure on the space x, and this measure is in fact a probability measure. So this is really kind of fully specify how random this value is, and this thing is used purely for the kind of the code analysis if you want to transform the code and kind of reason about the code. And then the last field is just the pseudo-random generator. So when you actually compile the code and you want to run the stuff. So for example, using this object, you can write a probabilistic program like this, where you flip a coin with a probability theta, you get some Boolean variable, and then whether it's true, you return 0, or if it's false, then you return some value. So here's, I have a code like this. And what this allows me to do, for example, I can define the mean of this. I might be interested in what is the mean of this program, right? So I just say, okay, I define this function and I take this random program and I say, okay, I want to compute its mean. And the mean is again defined by some integral, which is completely uncomputable. So to actually get something I can evaluate is that I call a rewrite by. My goal is to compute the mean of a test theta. I unfold the definition. And then again, I have a bunch of theorems that can easily kind of look at a probabilistic program and then infer what the mean is. So you just apply a bunch of kind of transformation rules, and you get the result that like the mean of this program is this expression. And I can here actually run a test. So for example, yeah, like for particular theta, the exact mean is computed should be like this value, and this is by actually executing kind of really running the pseudo-random generator, I get the estimate of the mean is this with this particular variance. So while I'm talking about probabilistic programs, I want to show you, I think, like very neat application of Lean and probabilistic programming to solve Laplace equation. So I would like to solve in some domain omega equation that the Laplacian of the function u is 0, and then at the boundary of this domain, it satisfies some given function. So any function that satisfies that the Laplacian of the function is 0 has this funny property that if you look at the value at some point, you can take the average of all the values on a sphere surrounding this point, and these things are equal. We can exploit this to actually construct a probabilistic program that will compute, that will actually solve this equation. So first, we can kind of look at this equation recursively. So if you want to know the value of this function at this point, we can compute the average over this sphere. But to get the values over this sphere, we can again compute values over this sphere, and then on top of this sphere, we can, on this sphere, we can compute again the average over this sphere, and you can see the trend that this sphere is actually converging. It's getting smaller and smaller and converging towards the boundary. Right. So in the limit of this process, we can just evaluate the function g. So we can define this function un kind of recursively, where we always take the average of the values in the previous iteration. And in the 0th iteration, we just say, because we kind of expect that at the 0th iteration, we will hit the boundary. Right. Yeah. So at the 0th iteration, we kind of hit the boundary, so we can just evaluate it. Okay. I'm not expecting that you actually followed all of this. The only important thing is that I have this function un, which is recursively defined through these integrals. And what I'm interested in is actually kind of looking at the limit of this function un when the n goes to infinity, and I want to evaluate this. And the hope is that this function will give me the solution of the Laplace equation. And the next step is look at all of these integrals and approximate them. So any integrals, somehow you can think about it as an expectation. So what I can do, I can generate random points on this sphere and then just evaluate this function un. And if I write this in this whole recursive definition in terms of expectation, I can actually generate a probabilistic program that I can execute. So let me show you the code. So okay. So the initial crucial definition is this line where I define the un in terms of all the previous and in terms of like computing the average over a sphere. And this thing corresponds exactly to this definition in Lean. So I have this function, I call it harmonic recursor, and you are provided a function which computes the distance towards the boundary of the domain, and then here is the function that gives you the boundary condition. So at the 0th iteration, you just return the boundary condition, and in all the kind of the successive steps, you compute the average over a sphere of the previous iteration. Okay. So the only thing kind of interesting is here is that this is a function which is recursively defined and has a bunch of integrals, and I want to turn it into something that I can actually run on a computer. So what I do is that I define this function walk on spheres, and I say, please derive a random approximation of this function harmonic recursor. Okay. And then here again, I have just a bunch of tactic. It's just effectively instructions how to turn this thing into something I can run. And this macro derivation approximation, it says, please rewrite this into form that it should be expectation of some like a probabilistic program. And then I will give you the probabilistic program and give you like a proof that if you compute the expectation of the probabilistic program, you get this value. So our goal is to somehow rewrite this expression into form that it's expectation of some probabilistic program. And because this function is defined by an induction, then we effectively have to rewrite this expression by inductively. So in the 0th case, we split it into 0th case, and in the successive state step. So in the 0th case, we just unfold the definition of the harmonic recursor, and we get the function g, and it's just the function someone gives us how to specify the boundary condition. So the more interesting case is how to do it in the successive step. And you can already see here that because we are doing induction, we have an inductive hypothesis. So we know that there is some function previous, and we know that this function is actually equal to the harmonic recursor. So, and we are interested, so at the harmonic recursor at n, at the iteration n, and we are interested for the value of the harmonic recursor at the n+1. So what we do is just unfold the definitions. And what we are faced with is integral of, effectively we are integrating over a sphere this function previous. So what we do is that we just approximate this integral by, no, we don't approximate it. Like this integral can be written is equal to taking a uniform samples over a sphere and then compute the expectation of some function. So we rewrote it, the integral as expectation. So now we kind of zoom out and again, the only important thing here, we are doing some kind of recursive definition, and in the recursive definition, we are computing expectation. So we are kind of recursively computing expectation, and there I have a theorem which effectively says if you're recursively computing expectation, what you can do, you can compute expectation of a probabilistic program where you draw the samples recursively. So if you apply this theorem, you end up with, oops. You end up with the goal that you are computing a mean of some probabilistic program. And now it's in the state where this macro is very happy because it's exactly expecting that we provided some expression that is, please compute a mean of some probabilistic program. So what this macro just does is it returns me this probabilistic program. So now this function Walton spheres is some probabilistic program which has a guarantee that if I compute its mean, I get this value, which I didn't know how to compute previously. So to kind of demonstrate that I can actually that this function actually works and computes what I'm expecting. So just so Laplace equation, for example, one thing like physical process, it can model is how heat distributes throughout the space. So here I wrote like a funny test where I have this piggy, which has very hot ears and very cold nose. And I would be interested in how the heat actually distributes throughout the space. So I actually wrote a plugin into this program, which is something like a Blender, which allows you to use Lean as a scripting language. So here you can actually see I have some node which has a bunch of Lean code, which is exactly running what I was showing you before. And I look at kind of, I initialize this grid, this square, and I would like to evaluate the temperature on this square. So you can see that if I look inside of the ears, the ears are kind of warm, and then it gets kind of colder while you're approaching the nose. And because it's random approximation, I turn in the probabilistic program that you can see it's noisy. Ideally, if I would refine the number of samples, this would get smoother and smoother, but it should kind of, in the limit of infinite samples, ideally it computes the solution of the Laplace equation and effectively how the heat distributes throughout the space.
So you think two-dimensional, like if you can't through the three-dimensional space with the two-dimensional.
I have very hard time hearing.
So I think the question is, how do you get the discretization?
Discretization of what?
Of the object that you're looking at.
Oh, of the object. So the object, the software has a like some polygonal approximation of the object. Right. So in this code, right? So I'm effectively evaluating this function while doing this. And this function, the only thing it needs this distance function, which computes, given a point in space, give me the distance towards the object. And I'm just reusing the machinery of the program that if you have a triangular mesh, then for every point in space, it can give you the distance to this object. And that's effectively the only kind of discretization, or this is the only description of the object I use. And then you also need the function g, which tells you the temperature on the object. So what I do, because this function is somehow, for technical reasons, I define it everywhere in space. So if you ask for it in a space, then I look at the closest point on the object, and then I just read the values which I defined on the object. So,
does that answer your question?
I was mostly wondering if the measure wasn't a two-dimensional surface because there was this square.
Oh, so I have to. So this square, right? Where is it? Is it? So I can. Right. Yeah. Okay. This is. Let's see. So I have to take somehow where I evaluated the function. So I can take this thing and I can move it. What about -1? It takes some time. Oh, okay. I can just move. I can just move the plane around. So yeah, I just have to pick a plane where I actually evaluate the solution. So I pick this plane. So or maybe I can. Yeah, I can rotate it by 90 degrees. So you can get the slice this way. Right. Right. So these are all the kind of examples which hopefully I kind of convince you that Lean can be interesting for doing scientific computing, and do stuff which I think is very difficult to do in other programming languages. But I have to worry, almost none of it what I wrote down is fully formalized. I usually try to kind of any source code transformation, I kind of try to dissect it in a bunch of theorems, which I just state and then do not prove, and then just kind of combine all these theorems. But right now I do not attempt in like proving all the theorems such that the whole transformation is sound. And maybe kind of like the interesting point, which I found out, because at some point I try to actually proving all the theorems that I'm using as is that all the math that is formalized in MATLAB I'm running into issues, and I kind of found out that the standard mathematical notions are not always useful when you do transformation of a source code, and the reason is that like in my experience in mathematics, for example, people very like to use objects like Banach spaces, manifolds, or when integrals using like a strong version of integral or measurable spaces. And these things have if you do some kind of program transformation, they don't have that nice properties. Mostly the problem is that Banach spaces, for example, if you take a space of like differentiable functions between two Banach spaces, then it's not a Banach space. Again, if you take a space of like all the functions between two manifolds, you do not get a manifold. So in dealing with programs, you really need to have very good notion of a function space and such that it has a nice properties. The same way when using the Bochner integral, you can integrate only functions that has values in some vector space that has a norm. Effectively, it's a Banach space. So sometimes I was, in all those examples I was showing, that sometimes I was integrating functions integrating functions that have values in functions, and these functions really do not live in spaces that there is a norm. So you probably need some weaker notion of integrals. So ideally, instead of Banach spaces, I would like to use, for example, the notion of convenient vector spaces, where all the automatic differentiation would be much easier to formalize. Or instead of using manifolds, I would like to use diffology, which is again some generalization of notion of manifold, where you kind of guarantee that you are working in the Cartesian closed categories. So like you have very nicely behaved function spaces. Yeah. And I think, for example, when doing the probabilistic programming, people in the programming language community, instead of using measurable spaces, they use something what is called like quasi-Borel spaces. So which again has much better properties in terms of like the function spaces. So that's kind of interesting that I found out. So yeah, with this I would like to conclude the talk. So I'm working on the library Silene. All of this code is there. You can find it at this website. I started writing like a book/documentation about it, but it's very early draft. So right now there is only one chapter, and it's talking about how to use arrays. So there's not that much to note. I think I would like to point out like kind of my design principles when designing this library is that, like, first and foremost, I'm interested in creating a library that's like very usable, very composable, and very general. And even though I'm using Lean, the formal correctness right now is not the main focus, because first I need to get something that is usable, then that it actually runs reasonably fast, and then I can worry that it has actually these nice formal guarantees. Yeah. And I would like to conclude that that Lean is really cool new language that has very cool features which were originally designed mainly for theorem proving, but I think they can be exploited for scientific computing, and there is like a vast new design space which should be explored. So yeah, that's everything from me, and I'm happy to answer any questions.
Thank you very much for this really interesting talk. Do we have questions here in Cambridge? Yes.
Just to get an idea, like, should I be thinking of Silene as a package or a library to do scientific computing in Lean, or can I use it or things like convergence theorems or foodies or?
Can I get the question repeated, maybe from Jonas?
Can you come closer to?
It's the mic is really bad, or I have a really hard time.
Difficult on the other side.
I'm sorry.
I've shuffled everybody now. Hey, thanks for the nice talk. I just I want to see if I understood this correct. So are you thinking of Silene as another library or a package for the Lean language, or do you expect I'd be able to use this to show, let's say, if I have a stochastic ODE, that converges at some point or not? Like, is that the sort of things I can prove using this?
No. Like, my goal is to really be a library for doing scientific computing. So my hope is exactly that that I can kind of capitalize what is in MATLAB and effectively use the results from the MATLAB and then maybe provide some formal correctness in Silene. But it's really more, right now I would think about Silene as a library like a SciPy or like a Julia or something, and I'm really exploring the design space of what the dependent types can offer you in this regard, and what having interactive editor can offer you and stuff like that.
Can I follow it up with another question?
Sure.
So how are you keeping track of the numerical precision? I'm asking this because I'm kind of realizing that, let's say Julia or Python, like when we try to compute certain things, they're not quite precise. Like they really are horrible pretty much, like 3 decimal digits, and things start to diverge quite badly. So at times they're quite useless from a scientific computing point of view, because like particularly if I'm trying to get 10 digits of precision, fortunately I have to go resort to either C++ or something else. So here, how are you tracking? Like, is that something you have in mind where you're keeping track of like the precision parameters more explicitly in terms of digits?
That's a thing which I'm not really addressing. So right now, for example, all the proofs I kind of assume that I'm working with idealized real numbers, and then I just like close my eyes and run it with floats and hope for the best. So effectively, to get a reasonable answer is you have to kind of keep the good practices from normal scientific computing, such that, I don't know, you do not subtract two large numbers and hope to get a reasonable result. So there's definitely opportunity to provide some tools that would give you formal guarantees. It's a thing that I'm not expert in. I have very little knowledge about doing this. And I feel like there is loads of already existing work, like people are exploring exactly using theorem provers to kind of guarantee floating point arithmetic. But exactly doing automatic differentiation, I don't know, doing optimization, finite element method and stuff like that. I feel that there is not that much work on this. So I'm kind of really focusing on these areas and see what the new interesting stuff can be done there.
Do we have other questions?
Hi, thanks for the talk. I have maybe it's kind of a vague question, but as far as I understand, one of the difficulty with the usual scientific computing tools is that it's very hard to know when a certain method or function or something is actually going to give you sensible results. Mm-hmm. Because you have precise mathematical conditions on the inputs, and these are maybe documented somewhere in the manual or something, but there's no way of like expressing them really in the tool. And I have the feeling that things like what you're doing would be a very nice place to have exactly the two at the same time. What are the exact conditions on which these things work? So maybe even without having full formal correctness of a certain procedure, at least clearly documenting that this certain transformation works if the function is C2 or whatever, something needs to be smooth for this thing to work, and then you can kind of collect and at least give to the user the exact mathematical specification. So I wondered if you kind of thought about these kind of things maybe as a weak form of correctness, of at least stating the kind of conditions you need for things to be well behaved.
Yeah, that's exactly kind of, for example, I had this object approx, and I was exactly thinking that it would kind of store also, like the idea, you use a method, right? I don't know, you use a method or something, and then, for example, you have a guarantee that you actually converge if you have like strongly convex function or something like this, right? And then this approx object would be exactly kind of storing all this assumption you've taken, right? And then if the program is not giving you the right answer, they'll like this, you can actually query the approx object and it will tell you, oh, you actually assume this and this and this, right? And then maybe you have to actually like recheck that it's actually sensible in your case. Right? Or also the idea is that, right, like starting from the beginning, you write down some model, and then you kind of transform it into some code that is actually like simulating this, right? And what I'm really excited about is that you usually start with very simplistic model, right? And then you would like to kind of modify it, so you can add additional terms to your model, and then you can hope that all the transformation kind of go through. But for example, because you get some additional term which behaves differently, it can suddenly kind of warn you, hey, if you apply this method, that suddenly this assumption that this method assumes that like your function is monotone or something is not suddenly satisfied. And then so exactly, that's exactly what I would like to explore.
I think it's a very cool perspective to be able to do these kind of things nicely automatically and having it all in the same place, basically.
There's lots of work to do to achieve that, but that's definitely the direction. And of course, and then once the AI overlords come, right, then the transformation doesn't have to be done by a human, but it can be done by AI, and the AI can capitalize on this information and kind of maybe give you better stuff.
Thank you.
Last question.
Sure. I think mine didn't work from that. Well, now you're coming anyway.
Hi, I was wondering, you are building, if I understand correctly, a whole new library of containing physical constants as well to use in applications, like you had this example where you were approximating temperature, right? So I was wondering how you think in terms of library organization and in terms of naming conventions for all these new concepts you're using. Because I'm not a lean person, but I know that in lean you have very strict naming conventions for everything, right? So I was wondering how you are extending your library.
And maybe like MATLAB has a strict naming convention. I don't know. I feel like in my case it's a bit chaos. So yeah, it's definitely a challenge to kind of organize the stuff. I don't know. I don't think I can give you for example, I have loads of theorems about functions. So for example, I define a function and then I, for example, generate theorems that this function is differentiable in these arguments and the derivative of this function is in these arguments is this thing. So I have very kind of, I effectively, I think, automatically generate names of these theorems. It's just like usually the function, the name of the arguments, and then kind of the transformation I use. I'm not sure if I'm answering your question.
Basically, my question has two parts, one about the naming conventions and one about the library organization in terms of concepts. But I do realize it's something not easy to answer in a few. I agree. I think it must be a very research problem to decide how to organize all these. I was just wondering if you had any thoughts.
So I think, like, for example, so loads of the stuff I do, it kind of revolves about this function transformation. So I have like derivatives, to take a transposition and take a function inversion, or I don't know, taking isomorphism between like isomorphic types, like translating functions between isomorphic types of stuff. These are kind of function transformations. So I have like a bundled core of the whole library, which most of the stuff revolves about these function transformation, and then I have like a separate modules. And I think I have like a module which talks about geometrical shapes. I have a module, hopefully one day there will be like a finite element library. I have a module which exactly deals with like probabilistic programs. But I feel like I reorganize the stuff on like monthly basis. So yeah, it's really. It's a constant struggle, and I constantly redo it. Yeah, I don't have a good answer for this, and I don't have a good plan.